A 3D city model is a digital representation with 3D geometries of the common objects in an urban environment. It should be noticed that the buildings are usually the most prominent objects that you have in a 3D city model, and actually many 3D city models are formed only of buildings. What's very relevant in the context of this lesson is that the formats and the structures of 3D city models will vary greatly between datasets, if these datasets are from different cities or different countries, for example. And this has to do with the fact that many different acquisition and reconstruction techniques can be used to create 3D city models. We can, for example, use procedural modeling, or we can decide to have an airplane or a helicopter collect elevation points with LiDAR, and then use extrusion to create a LOD1 model like that one. We can also use the same LiDAR dataset and use more complex methods to recreate LOD2 models. But we can also mount cameras on the airplane and take several photos from different points of view, and then use photogrammetry and dense matching of images to reconstruct a 3D city model like the one you see here. So this is called a MVS mesh, or a multi-view stereo mesh. And the part that you see here is one part of Helsinki in Finland. This dataset is openly available, so you can go and download it. The format of this 3D city model is a textured mesh. That is, we have a set of triangles that you can see here in orange, and each triangle has a texture attached to it. If a human is looking at this 3D city model, they can easily count the number of buildings, cars, trees, or street, for example. That's because humans can easily abstract all the triangles with their textures, cluster them, analyze them, and look at topological relationship between the clusters, and then they can easily detect objects. However, for a computer, this 3D city model is only formed by a series of triangles to which a texture is attached. This means that very simple queries for us humans to answer are very difficult for computers to answer. For example, if you ask a computer how many floors does a given building have, the computer wouldn't be able to do it directly. Or how many windows does the main facade of a given building have, it would also not be possible because the computer sees this dataset as only a series of triangles. A semantic 3D city model is a data model where only the relevant objects in a city and also the sub-objects or the sub-parts of these objects are labeled with their meaning, and these objects can have attributes attached to them. Conceptually, as you can see here, it means that a city is decomposed into classes that we deem relevant for certain application. For example, a city is decomposed into the classes building, road, tree, lamppost, etc. And each of these objects has its own 3D geometry and potentially several attributes. For example, attached to a building, you could have the name of the street, the name of the owner. The decomposition of the city into relevant objects is hierarchical, and the relationships between these classes are stored. You can see here that for the most important object or class in a city, the building, we don't stop the decomposition only at the building, but a building can also be subdivided, for example, in different ways. So you can see here a building that is a complex building that has an extension. So this building is semantically decomposed into two parts, and then each of the parts is formed by several surfaces that we call semantic surfaces. In the context of semantic 3D city modeling, the surfaces that are relevant for buildings are usually roof, wall, ground, and also doors and windows are very relevant. Also, what's important to notice is that this decomposition into semantic objects or semantic classes, each of these object or sub-object also has its own geometry. So we end up with two trees that decompose the city into semantic and object, and these two are linked. So we say that a city is spatially coherent if both the semantic tree decomposition and the geometry decomposition are coherent. That is, that every part in one linked to exactly one in the other one. You can see here the semantic 3D city model of the city of The Hague in the Netherlands. This 3D city model is in the format CityGML that I will explain in a second. And it's an open dataset, so it can also be downloaded and browsed. It's visualized with a specific software for 3D city models, and the software is called Azul. Notice that this 3D city model looks less realistic than the MVS mesh that we just saw of Helsinki, because choices were made. So the city was decomposed into two classes, basically, buildings and terrain, and trees, street, lamppost, and benches, everything that is in a city is ignored. For each of the buildings, you can see that they are semantically decomposed into parts if they exist, and then each part is also decomposed into semantic surfaces. So you can see that you can query the model to know which surfaces are walls or facade, which surfaces are roof, ground, and so on. And for each of these surfaces, you can also get attributes, and also each building or each building parts also has attributes that you can see in that specific software. To avoid the fact that every city or country defines its own classes to decompose a city, for example, that one calls a building and the other one a house, semantic models can prescribe the classes and often also the attributes that can be stored in the model. Of all the data models that exist for city, CityGML is probably the least bad of them. It's a data model that is standardized by the OGC, the Open Geospatial Consortium. It started around 15 years ago, and now we're at version 3.0. Notice that the name CityGML both refers to a data model that I'm explaining right now, but also to an encoding in GML, XML. I will explain that in a second. The classes that are possible in CityGML are grouped into different modules, as you can see here. So we have, for example, the core module where all the main classes are described. I will show it in a second. And then we also have modules for common objects that we find in a city. So for example, buildings. We also have one for the relief, for the terrain, the elevation, one for the transport, one for the vegetation. And we also have some other modules that are used by all of the other modules. For example, the appearance module that allows us to have textures. The specification and the description of each module is formalized in a document that you can see here, available freely online. And each module and each classes inside the module are described with text, but also the data model is described with UML models. As you can see here, the UML model can be pretty complex. This is the UML model only for the core module. So for the core module, we can see, for example, that we have a city model, and then this city model will have different city model members. And then if you follow the UML and you know how UML works, you will realize that a city model is formed of different city objects. So a city object can be a building, a road, a tree, a bench, and so on. And then each of these city objects can be represented with different geometries. So for example, with a solid or with a multi-solid. I will get back to that in a minute. And then if you look at the UML model for the building module, this is what we see here. You can see that we have an abstract building. So an abstract building is the parent class where we have that can be used to represent both buildings and building parts. If you remember, a few minutes ago, I showed a building that had a building part, an extension, for example. And it's also possible to represent the interior of buildings. So we have, for example, we have the concept of rooms, of units, and of stories. And it's also possible to represent with building installation and building furniture, it's called. We can represent, for example, balconies and chimneys. One particularity of CityGML is that it prescribes the different standard level of details for the 3D city objects. That means that every object can be represented in one of the 4 LODs, and we do that because different representation can be used for different application or different purposes. While all the city objects can theoretically be represented with 5 levels of details, in practice only those of buildings have been described. You can see here what is referred to as the TU Delft LODs. These are the 5 LODs which are further decomposed for having a more refined and more granular representation of the LODs. These are done for buildings. CityGML uses the international standard ISO 19107 for representing the geometric primitives of all the city objects. We have a full video and a lesson on exactly this topic. See the link below. And also CityGML supports textures and materials. So far, all the city models we saw were not using any of those, but it's possible to have textures and also materials attached to all of the surfaces of the 3D city model. Here we can see the 3D city model in CityGML format, textured, that is visualized with the software FME. And also you can see that we can query and remove surfaces and see the different properties of and attributes of all of the objects. For the first 2 versions of CityGML, released respectively in 2008 and 2012, the only encoding officially available was an XML encoding. Actually, CityGML was designed first as an XML encoding, and then the data model was linked to this encoding. The new version of CityGML, version 3, that was released in 2021, is different. The data model is independent of the encoding, and several encodings can be derived from it. But let's start briefly by looking at an XML file of CityGML. A file looks like this, so it's a text file. CityGML is actually an application schema of GML, which is the geography markup language, which is based on XML, and this is also standardized by the OGC. A typical CityGML dataset consists of a plain text file, an XML file like the one you see here, and possibly some other image files that are used as textures. These can be JPEG or PNGs, for example. Notice that this file has 2 buildings. For the first one, we can see that it's represented as a LOD1 solid, and for this building we also have its ID and also one attribute, which is the function. In theory, XML encoded CityGML files are great because they are text files that can be read both by computers and by humans, and they're very structured. However, in practice, things are a bit different. CityGML files are in practice very complex. They're deeply nested. It means that, for example, one building can have a building part that has another building part that has a building part, and so on. And this is not very good. In GIS, we like things when we represent to be flattened out. For example, in a database, for simple feature, things should be more flattened. And also, there's many ways to do one thing. So if you want to represent a solid, or if you want to attach semantics to the surfaces of a building, there are many different ways to do that. The consequences of having very complex files are that in practice, very few software packages will fully support the XML encoded CityGML files. One example is that to this date, even if CityGML was invented around 15 years ago, there's still no parsers in JavaScript that can parse or read a CityGML file. And also one problem in practice is that since there's many ways to do things, most of the files that you encounter will be structured completely differently. In 2018, because of all the problems that developers were having with XML encoded CityGML files, we, several researchers at TU Delft, decided to move away from XML and GML and encode our CityGML file, the data model, in JSON. And that has led to something that is called CityJSON. As you can see here, CityJSON basically becomes an alternative encoding to the GML encoding of the CityGML data model. Why we did this, we've explained it a bit in the video so far, but if you want to know more details, you're invited to go read and download this article, which is also an open article, so this is free for everyone to read. All the details of CityJSON are available at cityjson.org. There you have the reasoning why we did that. You also have the full specification. The schemas can be downloaded. We've converted automatically from CityGML to CityJSON several data sets, and we also offer them there. And we also are maintaining a list of software that can be used to read, write, and manipulate CityJSON files. We're currently at version 1.1 of CityJSON. That is, as I'm seeing this in January 2022. Version 1.1 added the support for CityGML version 3, which is the new version of CityGML, the data model. Actually, CityJSON supports around 90% of the features of CityGML version 3, and the rest of the features that are not supported by design. That was to simplify CityJSON and ensure that it stays simple, lean, and easy for people to use. What's also important is that since the summer 2021, CityJSON is a community standard of the OGC, so it's an international standard. And we also have open source software that can automatically convert between CityGML and CityJSON and vice versa. And we already have a long list of software that are supporting CityJSON. One particularity of CityJSON is that we have flattened out the hierarchy. So all the objects that we have, for example, building and building parts, are separated into levels, and each of the objects are all represented in one file at the same level. So we have basically flattened out the hierarchy so that developers can easily read, process, and write new CityJSON files. A CityJSON file looks like a typical JSON file. So a CityJSON is a JSON object that has several properties, and I will explain briefly what some of them are. So a typical CityJSON file will start with having the type CityJSON, and the version would be, for example, 1.0. We offer a metadata module, and our metadata are compliant with ISO 19115, which is the international standard. Notice here that CityGML has no mechanism in version 2 to have any metadata, but since we thought it was very important, we've added a metadata attribute, a metadata property to CityJSON, so that the metadata of files can be documented in a structured way. After that, we have the city objects. So as I said, we list all the city objects in a flat list, and all the city objects are indexed by their ID. So it's mandatory for city objects to have ID. So the ID of the first one is ID-1, for example. And each one of these objects can have a set of attributes and can have geometries. For example, here we can see that the first object is a building, that it has 3 attributes, so measured height, roof type, and also the owner. And also it has a geometry which is of type multi-surface, and then the surface is given by the certain set of boundaries, which are a certain set of surfaces in this case. Notice that the geometry that is stored in CityJSON is not exactly simple feature. So that is, we don't list all the coordinates XYZ, XYZ, but these numbers 0, 3, 2, 1, for example, in the first surface of the multi-surface, refers to the index in a list of vertices. This is similar to what many formats in computer graphics is doing. For example, OBJ, PLY, or OFF, they're all doing this. This allows us to compress the file because we're not repeating coordinates, we're simply linking or pointing to the same vertex, and we also add more topology to a file. And finally, as is the case with CityGML, we can represent textures and materials for all of the surfaces or objects that we have in the file. One particularity of CityJSON is that since we store building and building parts in a flattened way, so at the same level, then we have to have a way to link them. And this is realized with this simple mechanism. So every city object can have children and can also have parents. One nice feature of CityJSON is that we can, as I said, since we are using different tricks to compress the files, for example, by using the OBJ indexing, we can obtain in practice a compression factor which is around 6. So we took several CityGML files that were openly available. So there's a list of 7 here, and you can see what we did is that we took the CityGML file, we converted that automatically to CityJSON, and then we obtain a compression factor that goes between 5 point something to around 8. And a good example of the compression factor is with the city of Zurich. So for example, here we took the file of the municipality of Zurich in Switzerland, as you can see here. So this file is rather large, so without any texture or anything, this file is 3 GB. But notice that with all the spaces and tabs and carriage return in the file, we removed them all to be fair before the comparison. But just by doing that, we already saved 1 gigabyte of space. So basically this file, which is 3 GB, by removing all of them, we obtain a 2 GB file about. But the CityJSON equivalent, which is lossless, all the same information is there, is 292 megabytes only. So it means that for this file, we obtain a compression factor of 7.1 after removing all the spaces in the file. But if we took the original file as is available in the website, then we would have a compression factor which is above 10. If you want to know more about CityJSON, you can just go to the website, click on help, and then we offer several tutorials. One of them is the getting started tutorial, so you can just learn slowly about CityJSON by using files and some of the tools.